Okay. All right. I think to not delay things any longer, because I know it's the end of the 4th long day, but this is a really, really nice way to end today, I believe. It's my great, great pleasure to introduce Helen Crowley, who's going to present for us, for this audience, her Joyner Lecture, which is very, very worth listening to. I had the privilege of first meeting Helen actually when she was an undergraduate student in civil engineering at Imperial College. I didn't know her very well. She was a rather shy but very clever student. She graduated in 2000 and went to work in industry for a while, and then she was attracted to Pavia, near here, where Michele Calvi had founded the Rose School, and she was one of the first MSc students in earthquake engineering in that school and did very well. And then Helen stayed on at the Rose School to do a PhD under the supervision of Rui Pinho, who of course you all now know very, very well. And they asked me to join as a co-supervisor. And it was a great experience. Helen is one of those students who almost instantly became a teacher. I learned much more from supervising Helen than I possibly could have taught her. And it's been a fantastic privilege to collaborate with her over the years. She's a remarkably talented, hardworking, productive, and creative earthquake engineer. She's made some really major contributions in the area of earthquake risk modeling, vulnerability assessment, and seismic design code specifications. And it's been a true pleasure to watch her grow and flourish and blossom in her career. I'm not going to summarize all her achievements. It's sufficient to tell you, as most of you will already know, that she's editor of the Earthquake Spectra Journal, and she's currently Secretary General of the Global Earthquake Model Foundation, GEM, both of which are perfect testimony to her abilities and her achievements. I actually nominated Helen for the Joyner Lecture last year, and I wrote to a few people around the world, a few of the leading practitioners and researchers in this field, to ask for support. And all I asked, I wrote to a lot of people because I know people are busy and people maybe haven't had time, so I wrote to quite a few people and said, could you just write a note to say that you endorse Helen's nomination? And 13 people responded, but they all insisted in writing their own letters, bringing out their own reasons for why Helen was deserving of this award. And what really came out in that is that Helen is not only hugely respected for her work, but hugely liked as a person. She's a very congenial and pleasant person, a real pleasure to work with, a really great person to be in projects which she's leading. And I'm not going to take up any more of your time, other than to tell you one quick story from my own experience, which testifies that even a long time ago, she was already becoming a really outstanding researcher and presenter in her own right. In 2006, I was invited to Istanbul to give a lecture in national conference, a Turkish earthquake engineering conference. And the lecture was to be on the subject of loss modeling. And I felt, well, number one, I was so heavily committed I couldn't really go. But second, it didn't seem appropriate to me that I presented the work which I was only really a passenger in the development of. So I declined the invitation and at the same time recommended that they invite Helen in my place. And she went, and that was the last I heard about it. But then about a year later, I had a reason for some other, completely different reason for some projects to go to Turkey. And I spent a few days in Istanbul and in Ankara. And during that trip, I lost count of the number of Turkish colleagues who came up to me and thanked me for not coming to their lecture. And you'll see why now. Helen, over to you.
Well, thank you, Julian. Thank you for warming up the crowd for me there. It really is a pleasure to be here to present the Joyner Lecture today. Put the slides up, yeah. I've already given this lecture twice because I presented it at EERI's annual meeting, also Seismological Society of America's annual meeting this year in the US. But this is the first time I've been able to deliver it to such a large international audience. And so I'm really pleased to be able to do that. I've tried to cut it down a little bit. I did find it was a bit too long the first times I gave it. But after looking at what I've removed, I realized I'd actually removed quite a lot of the jokes. So don't expect to be having many laughs today, but I do hope that we can get you to the party a bit quicker. So let me get straight into the lecture. I just wanted to explain what is the Joyner Lecture before I begin. So the Joyner Lecture is really to honor Bill Joyner's distinguished career at the US Geological Survey and his commitment to the exchange of information at the interface of earthquake science and earthquake engineering. And I think this is an interface that I've found that I've worked at for a lot of my career between engineering, seismology and hazard and earthquake engineering. But I find it quite difficult to work at that interface because I find almost that I'm not really an expert in either domain. I've not developed seismic hazard models or ground motion models. I also don't consider myself a structural engineer. I'm not designing or retrofitting buildings. But for some reason, I've decided to talk about both subjects today in this talk, both seismic hazard and its use for seismic design codes. But the reason that I've chosen this is because what really links those two subjects is seismic risk assessment. And seismic risk assessment is really the place where I've spent a lot of my career the last 20 years. So you've seen the title of the talk, Why Seismic Hazard Modeling Has Become a Risky Business. And I've decided to separate it up into sort of 3 sections, 3 chapters. So in the first chapter, I'd like to talk a little bit about the evolution of seismic hazard modeling, specifically for seismic design codes. There has been some discussion in many countries, but specifically in Italy, behind the evolution of seismic hazards for seismic design. And I have been asking myself if some seismic hazard modelers and seismologists are finding it's become a little bit too much of a risky business to define seismic actions for engineers. So on that second chapter, we'll look at some of the criticisms that PSHA for seismic design has received. And then at the end, I hope to convince you all, if you're not already convinced, that whilst seismic hazard modeling should not be a risky business, it certainly should be a risk business. I've decided in this first part to focus on Italy. We're obviously here in Italy today, so it's quite pertinent to talk about Italy. Italy is really, from a seismic design perspective and seismic actions for seismic design, has a rich culture. It's really one of the first countries where seismic actions were defined in seismic design codes. Whilst I'm not Italian, and I think there are many Italians here in the audience, I was working out the other day while discussing with colleagues that I've actually been half of my life, 50% of my life, living here in Italy. So I think I am somewhat of an adopted Italian, and I hope my Italian colleagues will allow me to really represent and discuss the seismic actions in design in Italy. So we heard already from Professor Calvi about the importance of the Messina earthquake. It really all started back in 1908. This earthquake was particularly devastating, the most devastating earthquake that has impacted Europe, with over almost 80,000 casualties. And what happened a year later was that guidelines, a code was introduced in 1909 for the repair and the replacement of the buildings affected by that earthquake. And what you're seeing there is really the first seismic zonation map in Italy. So then those blue areas were the areas where these new regulations had to be considered. The regulations would limit the number of stories, there would be limitations on the width of the road, also on how the walls should be tied together. And whilst there was a mention of the need for buildings to have lateral strength, this was not actually quantified at the time, but that quantification came 6 years later. So in 1915, after more earthquakes, so in Arizzano, for example, with over 30,000 casualties in the center of Italy there, the seismic zonation map was updated, so more municipalities, those areas you see in blue, were added to this seismic zonation map. And for the first time, there was a quantification of what should be the lateral strength of buildings. And so for the 2-story building example I'm showing you in this slide, you would have to apply a certain percentage of the weight laterally to the building. And this gave, in a 2-story building case, a base shear coefficient, so a percentage of the weight that the building had to withstand laterally of around 15%. So earthquakes continue to happen in Italy, and you see there, I'm going to go through them, but you see that more municipalities are being added to the seismic zonation map where earthquakes were damaging. And in 1927, there was a distinction between two different zones. And the highest zone 1 is the areas which had had more damage from the earthquakes, where the macroseismic intensity was higher. And in this zone 1, you were still designing to those same lateral forces I showed before, whereas in zone 2, those areas which had been further away from the damaging areas of the earthquake, the lateral forces were only around 10%. I'm talking about an evolution of seismic design, but there was also somewhat of a devolution around that time, where some municipalities were actually removed from the seismic zonation map. They were declassified. And this was really due to pressure, political pressure, requests from those municipalities to be removed because of the economic impact of having to apply the seismic design code, and because they felt that they were far away from those damaging high macroseismic intensity areas from those past earthquakes. So I'm just going to go through, and you'll see that as earthquakes are happening, more areas are added to the seismic zonation map, either in zone 1 or zone 2, as a function of the lateral forces. Then in 1935, another devolution, a reduction of the lateral forces. So zone 1 reduced down to 10%, in zone 2 from 10% down to 7%. And we continue through with more municipalities being added, being removed over time, all the way up to the mid-70s. And if you're interested in this evolution of seismic design codes and seismic design actions, myself and a number of structural engineers around Europe, we put together a study on what was the evolution of seismic actions in different areas of Europe. And so what you're seeing in this map here is from 1910 up to 2000. We've calculated those Bayesian coefficients that were required in the design codes in all of these countries in Europe, and we've plotted those zonation maps. And this was very useful for us when we were developing the European seismic risk model, because we wanted to understand the vulnerability, especially of engineered buildings, and how that had changed over time, and we could incorporate this information both into our exposure models and into those vulnerability functions. But let's go back again a bit in time. So we left Italy, which was evolving its seismic zonation map based on where earthquakes had occurred. Instead, in the US, in the summer of 1966, that what we know today as PSHA was emerging, and this was very well described in the paper by Maguire, 2008. So I have some citations there at the bottom of the slides. So in the paper by Maguire, he describes how Alan Cornell, whose name also came up earlier in Michele Calvi's talk, met with Luis Esteva, who was from UNAM in Mexico, and they spent the summer together. They had been separately developing really what were components of PSHA, and it was probably that summer together and their discussion of their ideas which led to the landmark paper, which you know, the 1968 Cornell paper. And in that paper was the description of what is a probabilistic seismic hazard assessment. You see this figure frequently, these 4 key steps to PSHA, the definition of the seismic sources, the magnitude frequency distribution for each source, the ground motion models, which tell you the level of ground shaking as a function of the parameters of the earthquakes, the magnitude, the distance, and then combining these into what are known as hazard curves, so probabilities of exceedance of different levels of ground shaking. One comment that's worth making here is that in that 1968 landmark paper by Cornell, there was no mention of the aleatory variability, or what we call sigma, in the ground motion model. That's why I'm showing in that plot no sigma in the ground motion model. And while that was then, in the subsequent years, was considered in a number of PSHA studies and reports, it wasn't included in that landmark paper, and as we'll see later in the talk, this probably led to some of these early generation PSHA models not to include sigma. We saw also in Professor Calvi's talk this map, or a mention of this map on the right, Algermissen and Perkins. So in the 70s, national hazard maps started to be developed as the basis for seismic actions in codes. So both Mexico here and the US, and as was mentioned, this 10% probability of exceedance in 50 years was proposed. And when I gave this lecture at the Seismological Society of America's meeting in Anchorage earlier this year, it was mentioned to me that the reason for the 10% probability of exceedance in 50 years was actually because it was seen that the seismic actions, or the PGA with 400 that came out of that assumption, were very similar to what the engineers had been using up until that date. So there was a desire to not really change the status quo, and that's where that 10% probability of exceedance in 50 years came from. And as you know, we're still using that in many countries, especially here in Europe today. Let's go back to Italy now. And so we left off in 1975, where the seismic zonation was still very much dependent on where damaging earthquakes had occurred. Instead, in 1981, a group came together to really apply what was probably the first PSHA, national PSHA model for Italy. And this was used as the basis for the seismic zonation in 1984 code. Then in the late 90s, there was another working group that worked together to produce a probabilistic seismic hazard model. This did not actually ever find its way into a seismic design code, but it was included in this non-compulsory prescription after the 2002 Molise earthquake. And this, for the first time, there was a zonation map where every single place in Italy was considered to be a seismic zone. And so that modern capacity design principles, ductile buildings had to be designed everywhere in Italy. And then we come to what's known as the MPS-04 model. So this is the seismic hazard model from 2004. At least in 2004 was when the first results of that model were released, a PGA map with a 10% probability of exceedance in 50 years. And then over the subsequent years, a number of other outputs of that model were released, spectral ordinates for different return periods. And these were included after the L'Aquila earthquake, finally into the seismic design code in 2009. Just to show you briefly how this model, this MPS-04 model, is used in the code. So we have a grid of points over the whole country. I think there's between 10 and 15,000 points. And at each point, a uniform hazard spectrum has been computed from the PSHA model for a number of return periods. And then what is found in the code is the PGA, a spectral amplification factor, and then a corner period. And those three factors have been defined by trying to best fit a spectral shape to the uniform hazard spectra. So they vary across the country and with return period. So where are we today? It's been 20 years since the first results of MPS-04 were released. Well, we have had an update to the seismic hazard model in Italy since then. It's known as MPS-19. But unfortunately, this model has not yet been approved and approved for adoption in the seismic design codes in Italy. And it's a long story, and I think there are people here that are probably much better placed to describe exactly why that isn't the case than me. But I did want to sort of focus on one key aspect which I think has been a problem and from which we can learn from in the future. So this model went through a number of reviews, international review panels, but there was one review in particular by the Civil Protection Department, which, when they were reviewing the model and seeing actually how much it had changed some of the values of PGA with the 475-year return period, how they had changed with respect to the MPS-04, there was concern. And so there were requests to change the underlying PSHA model, to make some adaptations to that model, to get, in their words, results that were, or outcomes that were deemed more suitable for engineering applications. And so the PIs of that model, of that MPS-19 model, have responded with a paper in Seismological Research Letters, so that's Marzocchi and Meletti, explaining that PSHA deals with what it is, not what we want it to be. And so what they're trying to explain in that paper is that a PSHA model should be considered the best of the available science that we know today, earthquake science, and we should not be adapting that model to get the results that we want for our engineering applications. Now, they refer to this as the hazard risk separation principle, and that it's been violated because hazard modeling should be kept separate from then how that hazard model is going to be used for decision making. I'm not a big fan of that term, the hazard risk separation principle, and I think you'll see from my presentation that I really want the hazard and the engineers and the risk communities to work closely together. But I do understand that we should not be changing the hazard models to get the results that we want. One perhaps unfortunate outcome of this debate and this lack of approval of the model is that it's reignited a somewhat old debate in Italy on is PSHA actually an appropriate method to be used for defining our seismic actions in the code. And so this takes me on to this second part of the talk, where I want to talk about some of those criticisms which PSHA has received, especially from what's often known as the deterministic seismic hazard assessment community. These criticisms come from, therefore, other earthquake scientists, but also from the engineers and from media. And I think, fundamentally, a lot of the reason for the criticism is a lack of understanding of what PSHA is and its role within design codes. So while I was preparing for this lecture, I read a large number of papers. I've just put some screenshots here of some papers of debates around PSHA and is it appropriate for use in design codes defining seismic actions for design. And these papers are often comments, there's responses, there's opinions, there's a lot of debate in the literature. And when I asked Julian about this, he shared one of his responses to one of these papers with me. And I agree with his comment here that these papers are written in an engaging and lively prose that is a welcome change from so much of the scientific literature. Now, don't worry, Julian, I will specify that, in your words, is the only redeeming feature of these papers. But let's look at some of the examples of criticism that you find when you read many of these papers, or also that comes through the media or from engineers. So we hear that earthquakes have occurred in a low hazard area. So this is an example of a paper, I've focused obviously on this example for Italy, where the authors, I don't think you can read the text at the bottom here, but they say here that these successive Italian hazard maps forecast some earthquake locations well and others poorly. So they have put the locations of earthquakes on the hazard map and have said, well, some of these locations are in low hazard areas, so that's a poor forecasting of the earthquakes. So as we know, hazard maps are not forecasters of earthquakes. This is what, for example, Frankel responded in his response to this paper. It entails a misunderstanding of PSHA. They're not predictors of the epicenters of future earthquakes. Now, one thing you could do by looking at where earthquakes have occurred is to go and look at the underlying hazard model underneath that probabilistic seismic hazard map. And let's see if the earthquake has occurred in an area where there wasn't actually a seismic source, or perhaps the earthquake exceeds the maximum magnitude that is allowed for by the model. But we certainly can't be looking at the location and comparing it with hazard maps which are actually ground shaking. Another thing that happens quite often is when the shaking is seen to exceed at some locations the spectrum, and then there's papers and comments that the code has somehow failed. So this is an example of a comparison of some response spectra from recordings in L'Aquila and how they compared with the code. And back at the time, myself and some colleagues, we tried to explain in papers why this was not a valid comparison and why you could not invalidate a uniform hazard spectrum just from single recordings. Also, Julian J has also published, I put the links there, a number of papers to really try and explain very well why we can't do this comparison, and then state that the code has somehow failed. Apart from the fact that the UHS is an envelope of spectra, and so we're really comparing apples and pears. But remember that we said earlier that we have targeted a certain probability of exceedance, perhaps 10% probability of exceedance in 50 years. So we expect our uniform hazard spectra to be exceeded. The problem is if it's being exceeded too frequently. And so in those papers that I cite there, there's a discussion of how we could start to evaluate the hazard maps. Now that we have a lot more ground motion recordings and data, we could start to see if we are exceeding more frequently than expected the uniform hazard spectra. But we certainly can't take a single event and a single location and start to criticize the spectra. And finally, it's been also in the media mentioned when what's seemingly a modern building has collapsed, that this is a sign that the code, that the hazard underlying the code has failed. And instead, as far as I'm aware, and when I'm giving this lecture, I'm inviting people to also give me examples if they exist, but as far as I'm aware, we don't have examples of modern, ductile buildings that have been designed with capacity design to the latest code that have collapsed due to earthquakes. Those that have collapsed, for example, in Turkey last year, it's been shown to be due to deficiencies, either in not properly applying the code or in the way that the buildings were then constructed, not following the right practices. So we know that design codes allow us to have a lot of redundancy and conservatism in our design. We have, as we heard earlier, we have capacity design. We make sure that our beams are failing before the columns in the buildings. We're going to stop these catastrophic failure mechanisms from occurring. And so seeing a modern building that has collapsed, as we can see here, we certainly cannot be then claiming that this is a failure of the PSHA model underlying the code. But while I was preparing the presentation, I was thinking, well, is there a reason that perhaps engineers could criticize a bit the PSHA community? And maybe the fact that hazard estimates do seem to have increased over time can certainly cause headaches for engineers who have to account for this adaptation in seismic actions. So if we go back to the early years of PSHA, I think probably we were not seeing so many big changes in the outcomes of the PSHA analyses. But as is well described in this paper by Bommer and Abrahamson, around the 90s, you did start to see a sort of a shift, an upward shift in the outputs of our hazard analyses. And this was because it became much more standard practice to include the sigma, the aleatory variability, in the ground motion model. And I don't have an image here, but you can imagine a hazard curve. What the sigma will do is that it will lead to larger values of ground shaking at larger return periods. What then happened over time is that we continued to collect more and more data. Somewhat paradoxically, this then led to an increase in the sigma in those ground motion models. You would imagine that it would decrease with more data, but it turned out that those early ground motion models, because they were based on limited data sets, they were really undersampling this scatter in the residuals. Another thing that was more common practice was to include epistemic uncertainties in the PSHA models. And epistemic uncertainty describes our lack of knowledge. But again, with more data, we would expect that with more data, we could reduce our epistemic uncertainty. But instead, this example is from a project in Switzerland for a nuclear power plant. This was a PSHA study from the 1980s, where you can see there the epistemic uncertainty, which is shown by the red arrow, the width of the hazard curves. It's quite narrow. So there was quite an optimistic view of what was not known at the time. Instead, when this study was repeated over 20 years later, with a lot more data that became available, the modelers realized with that additional data, they didn't actually know as much as they thought they'd known. And so they were increased much more their epistemic uncertainty. Now, the impact of that increased epistemic uncertainty doesn't change so much the median. I think if I flick between, you can see that dark, bold dashed line in between is not changing, but it is increasing the mean of the hazard curves. And that's because the mean is being driven by the tails of our distribution, which is now wider. So I've been asking myself and asking colleagues, and I asked this when I presented the lecture, might we expect going forward? I would like to think that with more data, we could actually reduce the epistemic uncertainty, but a lot of seismic hazard modelers have told me that no, you can expect the epistemic uncertainty to continue to increase. We still haven't really got to the place where we have a stable handle of all the different sources of epistemic uncertainty and how we're modeling them. There's also correlations in those epistemic uncertainties that are not being necessarily properly handled right now. Sometimes we reduce the epistemic uncertainties and we model them as aleatory just for implementation reasons in a PSHA analysis. So I think potentially we could start to see mean hazard results increasing in some areas because of this. But what does it matter? What does it matter to whether there's a change from one model to the other, and how much? When does it matter? When does it start to matter? So there have been a number of proposals put forward, mainly by PSHA modelers, to see whether a change in hazard is significant. And in a paper that we published earlier this year, we applied some of those methods. These are 4 methods that we applied. We looked at different PSHA outputs over time, and we compared them with these methods. So some of these methods look at simply the change in the PGA for the different methods at a given return period. Others are considering the epistemic uncertainty. Some are considering the whole hazard curve. But really the conclusion that we draw in that paper is that whilst it can be quite useful to have these methods to see where there are large changes or significant changes in the hazard, this can be useful to allow you to find out where you should be perhaps putting more attention in your PSHA model to try and identify why is there now such a significant change in the hazard. What we really need to be doing is evaluating the changes, not just by looking at the hazard, but obviously by looking at the way that they're used, their impact on seismic design and on risk. So let's move into this last section of the talk now, where I want to focus on why hazard modeling and the evaluation of hazard models should be a risk business. So the importance of changes in hazard can only really be answered, as I said, in a meaningful way within the context of risk. So I want to give you some examples of how we have been doing this, and we have thought about this over the years. So back in 2007, whilst the Italian MPS-04 hazard model was being developed, so we had those first results in 2004, but then more and more response spectra, uniform hazard spectra were being developed. We wanted to look at what the impact of that new model could be to the assessment of existing building stock in Italy. So we were comparing the practice of applying just those 4 different zones. Each zone had a different PGA value and a fixed spectral shape. And what would happen if we instead introduced the MPS-04 code, which had a much higher grid of values and where we had the uniform hazard spectrum changing with return period. So we took a number of reinforced concrete buildings, we applied the code, we applied a nonlinear static procedure, and we placed those buildings across the country, and we saw how many of them would be non-compliant. We brought in here also the census data to look at the number of reinforced concrete buildings across the country. So based on that 2003 simple zonation, we were estimating around 40% of the reinforced concrete buildings would not be compliant. Instead, when we introduced the new model, the MPS-04 model, this reduced significantly to around 16% of buildings being non-compliant. And this was an interesting conclusion because it seemed to suggest that large-scale retrofitting would be much more achievable should this new hazard model be introduced. And there has been a lot of buildings that have been retrofitted since then. There's also been a lot of buildings that have been designed to that code, to that MPS-04 seismic hazard. And I think that potentially the review panel I mentioned earlier, they might have worried about what would be the implications of now introducing the MPS-19, given that we've only just designed or retrofitted buildings to MPS-04. And what we've done is tried to look at what the implications of that would be within a risk space. So we assumed that all of our buildings have been designed or retrofitted with the MPS-04 hazard model. Then we produced models of designs for those buildings. We produced fragility functions. In the example, we were taking mid-rise reinforced concrete buildings. So we were producing fragility functions for buildings designed to the code. And then we were combining those with the hazard to calculate the risk. And so this map is the probability of collapse in 50 years and how it varies across the country for buildings that are designed to the code. This is referred often in Italy to implicit risk. There's been a big effort in Italy to bring together the community to look at this implicit risk from a number of different types of buildings, and I've put the reference there where you can find out more. But we were just looking at just a single building class more to demonstrate what this might look like. So for this mid-rise reinforced concrete building class across the country, you can see that the risk varies, but in almost all of the country it's below 1%. If we then revise our view of the hazard and we assess now with the MPS 19, we can look at what is now our understanding of the risk, our current view of the implied risk. And so whilst it has changed, it's still below 1% in all of the country. So if we took 1% as a sort of an acceptable threshold, it seems that designing buildings to MPS 04, even with our new view of hazard, we still have an acceptable level of risk across the country. So I'm not saying that this is what the outcome should be, but one of the outcomes you could take from this is that you could continue to design to MPS 04 because it implies an acceptable risk still. So should we change the seismic actions? And I think what I'm trying to say is that you need to do these types of analyses. You need to look at it within the risk outputs to really make those decisions. And you can't just look at the hazard results and criticize the hazard and try and change the hazard model. So one final thing I wanted to just touch on was how we thought about fully integrating risk model into the process of defining seismic actions for design. So not just evaluating those changes in design, but how could we actually use risk assessment to define how much we should be designing our buildings for. So back in around 2005, probably around the time that I went to Istanbul that Julian mentioned, we were thinking about quite a radical way in which you might design buildings in the future, and that you would calibrate the seismic design codes using a loss assessment. You would do a loss assessment, and you would not give the engineers at all a hazard model. So let me show you what we were proposing. So you would take a number of standard designs for a typology, let's say reinforced concrete mid-rise buildings, and I would take a number of standard designs and I would produce fragility and vulnerability models for those standard designs. We would also need a hazard model for the region where we wanted to design those buildings. So we were looking at Istanbul, and we had a PSHA model. And then what we wanted to do was do a regional risk analysis and calculate, if I put those buildings everywhere in that region, and then I calculate the impact in terms of loss exceedance curves, what might that look like? And this was probably one of the very first applications of the OpenQuake engine. This was over 10 years ago now. And so what we were doing was we were running what's known as a stochastic event-based risk analysis. We were generating long catalogs of events. For each event, we would calculate the ground motion fields. We've put all the buildings everywhere according to one of those standard designs, and then we're calculating the damage and the loss, and we're summing up all the losses. And then that leads to these loss exceedance curves. And so our proposal is that you could then, from these loss exceedance curves, discard some of the designs because they were unacceptable. They were leading to losses that were unacceptable. But I think we realized quite quickly that this was probably too extreme, probably too radical to completely remove seismic hazard from the code. And when I went to USGS around that time, I spoke to Nico Luco in his office, and he was telling me about what they were doing in the US. And that was, I felt, much more practical. Whilst they were not considering the group risk, the impact to all buildings in a region, and they were still considering buildings as individuals, they had a much more practical way to bring in risk into the calibration of the codes. And many of you will probably be familiar with the risk-targeted seismic design maps. So I have a few slides just to explain them, just in case those of you in the audience are not so familiar. So the idea is that you have a single location, you've got your hazard curve from your PSHA model. Now at that location, I'm going to have a building that's going to be designed to the code, and it's going to have a certain fragility. And let me just put in a random fragility function, because I haven't yet designed my building. In the case here, this is a log normal distribution. It probably doesn't look like a log normal distribution. That's just because the y-axis on the right side is log normal. But that blue curve is really just a typical log normal fragility function. So let me now combine that hazard curve and that fragility function and calculate the probability of collapse in a given time frame. So if I calculate in 50 years, for example, with this example building, I've found it's 0.5% in 50 years. In the US, they've decided that their target acceptable threshold is 1% in 50 years. So this building would potentially be too good. So I could make it more fragile. recalculate the probability of collapse. In this case, it's 2%. It's too high. Let's keep iterating until we hit our threshold, our 1% probability in 50 years. So great, now I know the fragility functions that I want my engineer to design the building at that location to. The problem is we need to give them a deterministic process to do this. We don't expect engineers to be designing buildings and producing fragility functions. So what they did in the US is that they designed a number of buildings to different levels of seismic design. And what they found is that under the design actions, the probability of collapse was at most 10%, so around 10% or lower. So what we can now do is we can come into our fragility function at 10% and get from that our design actions that we need to design our building to. And so in this, for example, we would have a risk-targeted hazard value that would be 0.6 G. What I've been thinking about a lot is epistemic uncertainty, because hazard modelers continue to tell us about epistemic uncertainty and how this is not being considered in seismic design codes. And there are some proposals about how this could be brought in explicitly. I've cited some papers at the bottom there which are thinking about this aspect, that we could see those percentiles from our epistemic uncertainty as somewhat confidence intervals. So we could choose a certain percentile, and we could calculate a risk-targeted ground motion using that specific percentile. And so then we could almost target a uniform probability of exceeding our target probability of collapse, if you follow me. But this really requires a very stable modeling of the epistemic uncertainty, which, as I've heard, is not going to happen. So if we're expecting from version to version that our percentiles are going to vary even more than we're seeing our mean, I'm not sure that we should be using those percentiles specifically to target the seismic design. And also, let's not forget that we have a lot of epistemic uncertainty in the fragility. When we've designed a building to code and calculate the fragility, there's a lot of epistemic uncertainty related to some of the assumptions we're taking, the model uncertainty, how we're modeling the building, and this is often ignored. We would also need to bring that into the process. So I'm just leaving that out there as a question of an area where we need to think about more. Coming back to after we'd heard about this risk-targeted approach in Europe, we decided to look at it, how it would apply in Europe, and we realized that we had a lot of questions. We tried different values of beta, that's the slope of the fragility function, and we also didn't know at the time what was the probability of collapse under the design ground accelerations for buildings designed to European codes. So we made a number of different assumptions and really did a sensitivity study. So then some of my colleagues in Pavia and in Portugal, they started to look at this into more detail. So what is the collapse probability of European buildings under the design acceleration? So they took some standard reinforced concrete frames again, and they designed them to different levels of design acceleration. So from 0.05 G up to 0.4 G. Then they produced fragility functions for those buildings from nonlinear dynamic analysis with selection of records. And they also changed the geometry and the material properties. So what you're seeing there is, for different levels of design acceleration, a range of fragility functions for those buildings designed to the code, to the Eurocode. And then we can take, because they are log normal fragility functions, we can take the median value, so the 50% value, we can take the dispersion, and we can plot that and just see how that varies with design acceleration. And so I think there were a couple of interesting features of this study that came out. The first, as you can see there, is that up to a certain point, there isn't a change in the fragility function as we increase the design accelerations. So in this case, it was up to 0.1 G. This is understandable if you think that buildings are being at very low levels of seismic action. It's not actually the seismic action that is driving the design, but it's instead the wind loads, the gravity loads. This could be an interesting conclusion to present to hazard modelers, to say, we don't really mind too much how much your hazard is varying below this threshold, because it doesn't actually affect our design. Another interesting conclusion that came out was that the probability of collapse under the design acceleration actually increased with increasing design acceleration. So it wasn't fixed at 10% as has been assumed in the US. Thinking about this a little bit more, this probably makes sense. We've heard about displacement-based design just now from Professor Crowley. We were not using displacement-based design, we were using a force-based design. So we were not targeting a specific displacement capacity, and we know that collapse is driven more by displacements, and so we don't have a uniform probability of collapse. And so I think it's understandable that that probability of collapse is changing as the accelerations are increasing. So we decided to come back to the approach of in Europe of doing risk-targeted hazard now that we had these models. And we also wanted to bring back in societal or group risk, because when an earthquake occurs, it doesn't just affect that one designed buildings, but it's affecting communities of buildings. There's impacted, many buildings are being impacted. How could we also limit the impact on the larger scale when we're calibrating our seismic design codes? So we applied the risk-targeted process. In this example, it was Greece. We were using our collapse fragility functions for our designed buildings that we'd calculated for Europe. Then what we did is we calculated also vulnerability functions in terms of fatalities. And we placed reinforced concrete mid-rise buildings throughout the whole of Greece. And based on the risk-targeted hazard, we immediately had a fragility function, we calculated the vulnerability, and we calculated the losses using that stochastic event-based approach that I mentioned before. And so we produced loss exceedance curves, but not now for economic loss, but for fatalities. And here on the right, in the dark, sort of black bold line, the computed curve, this was the loss exceedance, or what's commonly termed as FM curve, that we'd calculated for buildings that were designed to code using a risk-targeted hazard approach. And what's useful about calculating these group risk metrics in this way is that many countries have standards that come from other hazards and other considerations. And so we can compare against standards to see if this is an acceptable group or societal risk. We could also incorporate epistemic uncertainty in this process when calculating this as well. What we might find is that our group risk is not acceptable, so we could then go and change our individual risk target, that probability of collapse in 50 years, and it could be an iterative procedure until we're happy both at the individual level and at the group level. And by talking to some colleagues recently, I found out that there was also a paper in New Zealand where they have actually, with the development of the new National Seismic Hazard Model in New Zealand, they have been looking at these concepts of targeting both individual and societal risk when defining the seismic actions in design. But I have been questioning, when preparing this presentation, should we really be using collapse and fatalities as the metric that we use to calibrate our seismic design codes? I mentioned earlier that I don't think we've seen any buildings that have collapsed and caused fatalities that have been designed and constructed to modern seismic design principles. So should we really be calibrating codes using assumptions for which we have no data, for which we can't really validate our models? And probably here, I think at the conference, many of you have been hearing about functional recovery, and I think perhaps the direction we need to move to is to shift down and to focus more on those lower limit states of damage. And potentially our group risk metric or our individual risk metric might be recovery time. So what, for example, is the total recovery time for the impacted buildings? And here we would really need the policymakers to start to think about what are the acceptable levels for this. So just to conclude, to bring all together the different components that I've mentioned and some conclusions. So I've talked about the use of national seismic hazard modeling and how it really needs to be within a seismic risk framework. To calculate the seismic risk at the national scale, both for individual and group risk, we need exposure models. We need models both of our existing building stock, but also where we expect to build in the future and what types of buildings we expect to build. We also need fragility functions for different limit states, not just collapse, and consequence models. And we can put this all together, as we've seen, to either target the seismic actions in the code or at least to evaluate the changes in seismic actions. One thing I haven't spent too long talking about, but one thing that I think would be beneficial would be to have software to simulate design much more rapidly so that we can look at these, the effects of changes in the seismic hazard on the design. And this is something that there's a number of open source software and initiatives that are looking at putting together simulated seismic design software. Another thing that we shouldn't forget is not just the hazard that changes from one version of the code to the other, but there are also changes taking place within the design code itself. And so by having a simulated software, we can also look at the impact that those changes in the design code have on the risk. So it really needs to be all brought together so that we're evaluating both hazard and seismic design code changes and how that affects the risk. And just putting on my GEM hat at the end here, we do develop a lot of open source models of hazard, of risk, and software, and I hope that we can facilitate what I think should be a very continuous feedback between engineers and hazard modelers on what are the impact of changes in the hazard on the risk whilst the hazard models are being developed. So just to conclude, I believe that the hazard science should be allowed to evolve. We should not make hazard modelers feel like their work is not worth the risk. They should be allowed to explore all of those scientific advances in the science, and the hazard model should be allowed to evolve over time, but that we should work together as hazard modelers and engineers to continually evaluate the impact of those changes on both the hazard and the design at the national scale. And as I mentioned, I hope that open software models can facilitate this. So I have many colleagues that I would like to thank that have worked with over the years. I don't have time to list them all. As you saw at the bottom of my slides, I had a number of citations, so please do check that QR code and you can see all of the people that I've worked with that I'd like to thank. And I'd like to finish by also thanking you for your attention. Thank you.